then someone else suggested, oh, what about the Anopheles mosquito or that other terrible payload from that mosquito, which was malaria? And you can see here that the map of malaria is essentially a map of Burkitt's lymphoma. So here was the first big giant clue. Now, there was a whole separate track. So in 1960 or 61, I think it was 1960, Dennis Burkitt had gone to London, to Middlesex Hospital, where he would talk about the crazy diseases that he would see. It was like the English surgeon comes in from the cold and tells all about the stories, or from the hot, I should say, and tells all the stories of doctoring in the wild. And they had this auditorium set up for him that seated 1,000 people, and 12 people showed up to this one of the stories. And one of those guys was a guy named Tony Epstein. Now, Tony had been studying infectious causes of cancer. And there had been all sorts of insight about the infectious causes of cancer ever since Tate Roos in 1911 had managed to passage the cells from a chicken fowl cancer from one to another, from a rock hen and from one to another. And he was punching out, of course, 60 years later he won the Nobel Prize. But there had been all sorts of analyzing clues. There had been, in the leopard frog and the loud cottontail rabbit and all sorts of other animal models. There had been evidence of tumors passing along by infection, but never in humans. And Tony Epstein was looking for some evidence of that and studying some sort of infectious agent. And so after the first of the speeches that Burkitt gave, Tony invited him out to tea. And hello. Why don't you, would it be possible if by any chance you could send some of your samples? Now, as I said, Burkitt was in Kampala, Uganda, and Tony was in London. And in 1960 or so, in order to send tumor samples, that far was a very, very difficult proposition. So of course, then Burkitt said yes right away. I'd be happy to do it. Once a week, there's a flight from Uganda, from Kampala to London, and on the night before, he would pack whatever specimens he could get from whatever patients he could get, packing wet ice and dry ice. It was an overnight flight. Tony would leave the flight in the morning, and then he would get a soggy batch of vials. And every once in a while, he was able to passage through some cells and propagate a cell line. And finally, he was able to find something remarkable in one of them with an electron microscope, which was kind of rare in those days. And here's what he found. He found Epstein-Barr virus. Now, of course, it wasn't called Epstein-Barr virus when Epstein found it, but later it was. And it turns out that Tony, and here's a picture of Tony, he needed some help, too, in sort of identifying, finding more of these viral titers in these cell lines. And he reached out to this guy, Sierra Koo, who had come to visit Uganda. Anyone recognize him? He was a former Surgeon General. You can see the same face, it's kind of amazing. So Koo had gone to Uganda and had come back and seen the Henleys, who had escaped Nazi Germany, they were in Sweden, where they were working on, they were phenomenal virologists in the husband and wife team, and they had some skill sets in identifying viruses themselves. And they said, if you want to work on the viral etiology of cancer, this is your chance. And so they took it up, and lo and behold, they found evidence of EBV not just in the cells, but in the nuclei of these cells, which is remarkable. And in fact, the more testing they did, the more powerful the evidence was that the Burkitt's lymphoma was, as it was now being called, was profoundly affected by EBV in some way. Now, a theory is emerging here, and we have one cofactor, one parasite, malaria red blood cells, with EBV, a virus that seems to affect, they didn't really know at the time, but bigger white blood cells. And how did these two things together transform the B lymphocyte, okay, at this point? And so this was a great big curious mystery that was happening, but at least something we were getting closer to understanding the truth. But that wasn't just the only thing that Burkitt was interested in. No, he was interested in curing this disease. So Joe Burkitt now was an early chemotherapist at Sloan Kettering in New York at the Sloan Kettering Institute, and they had remarkable success curing childhood leukemias, or at least bringing the long-term remissions in the early days, with a drug called Epifexix, the folate, that is a B vitamin essentially in the cells. And when Burkitt came to Uganda, here was Burkitt saying, oh, can I get some of that Epifexix, please? And so he tried it, and it didn't work. And then they tried cyclophosphamide, which was another new drug at the time, the early chemotherapy arsenal, and they gave it to this boy, and lo and behold, it worked. Incredible. Amazing audition. So at this point, another guy named Peter Clifford, who was in Nairobi at the time, he started to experiment using a lot of the, again, these were shotgun, one-arm things. I mean, people get arrested for that today. But I think they were trying whatever they could to save these kids and these fast-growing tumors. And lo and behold, this is a combination of Epifexix and cyclophosphamide. And this is, all these kids, 15 kids, all cured from Burkitt's lymphoma using this arsenal, this new arsenal of chemotherapy. Now, I went through that story, that very fast, incredible story, to give you a sense of timeline, right? So 9 years, that's all it was. 9 years from the very first discovery of the first Burkitt's patient, his first child. The who, the what, the when, the where, and all the names, 9 years. It's amazing. And all that remains were the how and why. this is, over the next 16 years, there were an awful lot of clues that were solved, a lot of mysteries that were solved on the how, right? So it turns out that this had everything to do with the oncogene mutation cancer, that the start of this disease was the human genetic oncogene. And you can see here what happens is that there's a little translocation at the bottom of the chromosomes between 9 and 21, 814, I'm sorry, that's the other one. And they create this sort of scary, powerful mutant protein called MYC, and then sends the cell on an endless double cycle. And so over the next 35 years, well, things change. Now, this is just Burkitt's lymphoma. I'm not talking about, we made some progress, obviously, and we're excited about a lot of it, and D-miners has mentioned some exciting stuff. But over the next 35 years, we made a little bit kind of stop. So Burkitt's lymphoma is only a little bit better understood, not much. It's still common in children, no prevention at all. It's still the most common childhood cancer in Africa. Its cost of treatment is prohibitive. Now, the actual cost of every one of these drugs, which are off patent, is about $50. $50 for methotrexate now to cure a child with, the curation center with methotrexate and cyclophosphamide. That protocol costs about $250, but it's still almost impossible to secure these children without that, because getting these families to the clinics that have these centers that can do the protocols is very, very difficult. And so my question is, what changed in between then and now? Right? What changed? Did anything change? It's just all in my head, but maybe it is. So to do that, I think what we want to do is we want to go back to Dennis Burkitt and imagine how a young Dennis Burkitt today would fare in today's cancer research realm. And to do that, I think it's important that we give him a good haircut and push him into the future. And so let's do that. So let's meet Dennis Burkitt circa 2017. Okay. Now, it's all for that slide, honestly. It's all for that presentation. It's all for that slide. Now all he needs, of course, is a research grant. Absolutely. Okay, apparently not. And really what that means is an R01. That's what it means. Back in 1980, the average age for a first R01 was 36 years old. This is now 42. The share of RPGs awarded to Research Project Cancer Death to investigators under age 40 was 40%, more than 40%, now about 10%. And you can see that the PIs, the principal investigators, that are younger than 36 are getting almost none of these grants. The share of PhDs getting tenure track positions within 6 years is lower. And by the way, I was talking with Dean Miner today about the roles of physician scientists in all this, which many of you will become or are. And it's even more challenging because you're 3 years behind everybody else. And you're also spending a lot of your time taking care of patients in the clinic. So to be able to do some of the research that you need to do is all the more challenging. And there have been one Blue Ribbon committee after another on this stuff. And so, but love shot or not, Dennis has to try. He's got to try hard, and that means he has to quickly back up some publications, correct? So, today's cancer realm, that means finding his own little tiny corner of the map. And when I say map, I really mean this map. Okay, how many of y'all know this map, right? So, there are places in this world where you can go and you see this on every wall in every lab. It's an old one anyway. But this is a summary map of cancer pathways. And so imagine if you wanted to study MYC, which was behind Burkitt's lymphoma. And what you'll see is, of course, this is that mysterious oncogene I mentioned. The only problem is the field is crowded. Okay, so how crowded is it? Well, this is as of a couple of days ago, 28,182 published papers in PubMed, and 740,000 results on Google Scholar. Now, why is this important? Well, it's important because every mentor that you have when you're young is telling you, hey, find your own little place and do your own little part of the puzzle and get expert in it. Because you do not want to be a middle offer type. You do not want to be an investigator in a crowd of other brilliant people. And you do not survive a career in academic medicine like that. So that's why it's important. And you can see 740,000 results on Google Scholar, and just to put that in perspective, this MYC has 12,900. So you can see some priorities there on Google Scholar. I thought it would be a little higher. Those are all academic papers, and they all start from this. I just like to show those just to show the importance of this. So we still haven't been able to translate. So all that acquired knowledge is significantly better. And so I just want you to know that I've been following 5 pathways, and these really the MYC and these others, just in terms of counting their published papers over the years. And PubMed doesn't have an easy way of doing it, so every once in a while I'll sort of look and weigh in and do the count. But that's an awful lot of published academic papers on just these 5 pathways in the medical databases. And this doesn't include, of course, all the hot new ones in immuno-oncology, and doesn't include the BCR-ABLs of the world and anything like that. So it's just, as I mentioned, every once in a while come down. This is almost 39,000 papers in the last 27 months. It's just these 5 pathways. So we're producing a lot of science, a whole lot of science. And then it's truly expensive. So back in 2005, David Lane was one of the co-discoverers of P53, the guardian of the oncogene. Managed to calculate that each paper costs $100,000. And then when I mentioned that to Ron Pino, who runs the Anderson Cancer Center, he actually laughed. He literally could not hold in a laugh. It's high risk, and it's like $200,000, $250,000 in terms of institutional money, Stanford money, and government money, and donor money, and whatnot. And then Vice President Biden was in San Francisco yesterday, and he talked about, 2 days ago, I'm sorry, and talked about each paper being about $200,000, so he may have different numbers than I have. But it's a lot when you think about that. So if you think about that, David Blaine had calculated that it costs about $3.8 billion just to study P53. And just to give you some perspective, we don't really have a complete working knowledge of this. There's obviously lots of tenderness includes. There's no effective treatment. There's something being tried in China, but we don't have a therapy based on this. And by Lane's calculation, this is what we spent on just these 5 pathways. Take a look at that just for a second. Let it sit in. Just in the producing of the academic medicine that this is important. And again, I think it's important. And so if the cost isn't about money, just more than money, it's about this is what happens to young scientists, right? So, Dennis, circa 2014, 2017, is just one paper, but many. You can't be just any journal, but top-tier journal or get those. You can't be just any place in the byline. It's got to be first author, right? Or senior author, last author. You need any edge you can get to get through this. This is the R01 review process. Actual R01 review process. Now, what is important here? Okay, I'm not going to read this, but I will tell you that somewhere around there, where's that? Oh, yeah, that little thing, 10%, for you. The benefit of my friends over here, 10% somewhere, there we go. Okay, that is what's important because that's the big line that somebody actually gets approved. That means that most of you go through this whole process, which takes a year or more to complete, and I'm not talking about getting your preliminary data, and I'm not talking about paying for your model systems and blah, 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 but a year or more to go through this process, and 9 to 10 of you want 9 out of 10 want to start over again. Because eventually you'll be out of the job. That is just the reality here. So, anyway, so what comes out of it, so what happens is the squeeze pocket comes out, right? So we get cautious, right? This is the danger. We start to think about what we know is going to get approved, what model systems already work, what's really, there's an old saying, the study session, only green light something you already knows the answer to. And this is some Nobel Prize winners and some others who are saying essentially that. Now, I can give you 50 of these sort of quotes from here, but this is a pretty established bit of wisdom to say. Unless you really have the answers to your questions, you will not be granted enough money to go and find them out. There's something bizarre in Heller life about that. Catch-22 life. So what happens is they shy away, right? They shy away from the federal agencies. They'll not worry about check. And from the Elijah report, which was intended to do just this, and they stop even proposing the radical ideas because nobody wants to be thought of as a sort of smart woman, yeah, but not enough preliminary work, or, yeah, but she really hasn't done the work. Nobody wants to be thought of like that. So, too radical, too out there. Yeah, we love to do this, but come back in 10 years when you're established and then try it. So this is the challenge here. And our young scientists get more and more frustrated. Well, what about collaboration and sharing? Well, there's no incentive to do that, right? You can't do what Dennis Bergen did because everybody has to protect their own little corner, their own little expertise. And then here's some headlines that I grabbed just together. This seems to be a little nature bias here. But this is just the kind of thing you see everywhere. These are well-known issues in our world. And so this is what happens. Hopefully not. I don't even want to encourage that. Get that kid out there. So what happens to our love safari? Can we unlearn the lessons of the love safari? Can we create a system that encourages scientists to compete rather than collaborate? To coordinate rather than share? To focus on the safe and narrow rather than on the risky and expansive and potentially paradigm shifting? And if so, what can we do about it? Well, I didn't read your culture makeover now. Dean Miner wrote a great essay in the Stanford Medicine fall, the fall publication that you guys have. And he said, he's spoken to a venture capitalist. He said, I will not invest in anything that requires changing human behavior, no matter how promising. And so, given that sort of Silicon Valley wisdom, how do we do this? Well, we do. We have to do it anyway. And I'm a believer in trying to force this kind of a cultural makeover. We need to stop talking about sharing, which we do all the time, and actually implement it, encourage it to do incentives. I'm not going to bore you all with a whole bunch of proposals there. And then we need to change our frenzy of grants and publication and start creating collaborative models. Now, there's some very exciting ones that Dean Miner and I were talking about between Stanford and Berkeley and UCSF, the BioHub. And a lot of these things are happening now, so I don't want to leave you all with the impression that none of this is happening. And in fact, this last idea, though, I think is the most radical. And the reason I feel comfortable saying it is that it comes from John Ioannidis, who's a Stanford guy, which is a fun project, not people, right? And we are, in fact, doing that here, or you're doing that here, with a Howard Hughes Medical Institute Light thing where you can grant people some unrestricted money and let smart people do what they do. And I have one of my colleagues here, Fortune here, and if I cater only for the projects that she did, only for the features, only for the specific brilliant stuff she does, and they're all brilliant, it would change the relationship. What you have to do, it would change what she wrote. What you have to do is say, hey, I'll go off there and figure something cool out, and come back with it and go pursue it. Now, not a very scientific enterprise, and if you're judging by success in industry, do not follow my industry. But having said that, I do think it's important that we need to change that. And I think we need to change this culture from within. And it's largely up to us, investigator advocates, physician advocates, donor advocates, patient advocates, industry advocates, academic advocates. We need to think of ourselves as change agents. And it isn't just about the money. It isn't just about saying, hey, we need more money for cancer research, more money for science. We do. We absolutely do. And I'll never say we don't. But what we really need is to change the way we spend that money and do the research and work with each other. And with that, I think we can save some more lives. I thank you very, very much. Thank you, Dean Miner. Thank you, everyone, for your patience. of course. Yeah, absolutely. Well, we have a few minutes remaining, and Cliff is very graciously volunteered to respond to any questions or comments you may have. We have a couple of microphones, so please feel free to come up. No? Yes, could you come to the mic? Thank you.
Hi, thank you for your talk. I'm curious about what type of incentives you were thinking about for people sharing their research.
Well, I think a lot of them are academic incentives, so it's important that I think the institutions where you are studying and beginning to identify, to fulfill a role, recognize that you're a team player. And right now, the incentives, although each department is different and every institution is different, as a whole, it's really about individual achievement and looking at what kind of grants you brought in. And they know down to the dollar what you brought in. And so how do we change that algorithm? How do we change the formula to determine that someone is a really brilliant contributor and plays off other people that do really well and has been incredibly valuable as a team collaborator. And I think we need to start working that into the academic system. And I think that part of this issue is sort of taking away the pressure of the publication.